Okay, so this is going to be a fairly short video. The next piece of the puzzle is this idea of reactance. So there's a new word for you, reactance. Now, I told you, and it was on the test, that if resistance is an opposition to current flow, then inductance is an opposition to a change in current. And while that's true, it's not quite the entire story. Okay, this opposition in the circuit is not the inductance so much as it is the inductive reactance. Okay, so reactance is the new resistance. Okay, so I started the first video by saying that in an AC circuit there are three loads of interest, not just resistors, but inductors and capacitors as well. Well, they don't offer resistance to a circuit exactly. They offer reactance. Now, it's still an ohmic value, okay? So, it's still very much like resistance, but it is reactance, okay? Which I think maybe before I move on introduces one more term as well, which I'm going to throw it there right now, and that is impedance. Okay, and impedance, which is also an ohmic value, okay, is a total of all of the resistances and reactances that exist within a circuit. Okay, so impedance is a combination of resistance and reactance all pulled in together. They're all ohmic values. Okay, so they are all different types of resistance as you've learned it in a DC circuit. Okay, impedance. But let's go back to inductive reactance specifically. Now, so resistance we represented with an R. Reactance we are going to represent with an X. Okay, and because it's inductive reactance, it's X subscript L. Okay, so a little bit of foreshadowing here. We're going to learn about capacitive reactance as well, and it's going to be X subscript C. Okay, so inductive reactance, X subscript L, can be calculated. So here's an equation for you. I showed you a couple of different calculations on the previous handout, actually this handout, the very first page, to calculate inductance, and I just brushed over it very quickly without even glancing at it. Told you there were other equations to learn, and here we are. So this is one we're going to want to know. So inductive reactance is calculated by, so first of all, it's 2 pi. Okay, and we're not going to worry too much about that. It's kind of like a constant. It's a recognition that we are talking about a sine wave, which is circular. Okay, we're kind of not going to think much harder about it. All right, but it's 2 pi, and the next variable here is f, which is frequency. Okay, and then finally calculate, multiply by L. So what is the inductance of the coil? So let's look at this. So how do we calculate the inductive reactance? Well, the sine wave. Okay, enough said. What is the size of the coil? So there are a number of variables involved in calculating L, but they're all about the physical characteristics of the coil. And then finally, it's F. What is the frequency of the sine wave? So if inductive reactance is an opposition to a change in current, okay, and capacitive reactance is going to be an opposition to a change in voltage, they're both in opposition to change. Okay, so one of the factors involved in how much pushback there is how quickly is that change taking place. Okay, an increase in frequency, because of the nature of the equation, an increase in frequency is going to result in an increase in the reactance. Okay, so the faster things change, the more we're going to push back against it. Okay, so that's the equation. I'm going to put a square around it to highlight it because it's pretty important. Okay, we can also manipulate this. All right, we could try to calculate for L based on XL. So if L were to remain all by itself on this side of the equal sign, XL remains right there, the 2 pi f is going to come across the equal sign and down onto the denominator. And so it looks like that. So L equals XL over 2 pi f. So let's try using the equation a couple of times just to see how these numbers work. Okay, so the example here shows we have an inductor with a given inductance of 0.8 henries. Okay, so remember inductance is expressed in henries, so there's our value for L. Okay, installed in an AC circuit. What is the inductive reactance at 30, 60, and 90 hertz? So let's see what happens as we increase the frequency of that AC waveform. So in the first case with 30 hertz, okay, it is 2 times pi times 0.8. Those variables are going to remain unchanged in all three of these examples. But in the first case, we multiply it by 30 hertz, and we get an answer of 150.8 ohms. Okay, so there it is. As I mentioned, reactance is an ohmic value, and so there it is expressed with its units, 150.8 ohms. Now we do the math again a second time. All the variables remain the same. The 2 times pi times 0.8 henries. This time we're going to multiply it by 60 hertz. And we can see that by doubling the frequency, we double our answer. We end up with 301.6 ohms of resistance. Add another 30 hertz so that we get to 90 hertz, and we're adding another 150 ohms and change to the answer, 452.4 ohms. So you can see it's a nice linear direct relationship. Increase the frequency, increase the rate of change, and increase as a result the pushback to that change. Okay, so let's leave this video there, a nice short one, and we'll come back and work on the next detail.